In 2004, two physicists in Manchester peeled a sliver of pencil graphite with a piece of ordinary Scotch tape. What they isolated that night was a sheet of carbon exactly 1 atom thick, and it broke physics. It is 200 times stronger than steel, more conductive than copper, and almost completely transparent. By 2026, it sits inside your phone battery, on stealth aircraft, in concrete, and in the world's most advanced chips. This is graphene, and the strange flatland of two-dimensional materials it just opened up. For most of human history, every material we use was thick, bulk metal, bulk wood, bulk plastic. Even our thinnest films, kitchen foil, gold leaf, are millions of atoms deep. Graphene is 1 atom, a material so thin that a stack of 3 million sheets would still be just a millimeter tall. Strip a material down to a single atomic plane, and the laws of physics it obeys quietly rewrite themselves. In the last 20 years, scientists have isolated hundreds of these atomically thin materials. Each one is a flat sheet of crystal, and each one behaves nothing like its bulk parent. They're stronger, lighter, faster, and stranger than any three-dimensional version of themselves. Today, the global market for these materials is $800 million and growing 31% every year. Samsung, Tesla, NASA, the U.S. Department of Defense, all of them are racing to find the killer application. By the end of this video, you'll understand exactly why and what's still standing in graphene's way. The story starts in 2004 in a basement lab at the University of Manchester with a roll of office tape. Two physicists, Andrei Geim and Konstantin Novoselov, were running what they called Friday night experiments. Wild ideas, no grant pressure, just curiosity about whether anything interesting could happen. That night their question was simple. How thin a flake of graphite could they actually peel off? They pressed a strip of tape onto a piece of graphite, peeled it back, and folded the tape on itself. Each peel split the graphite in half. They repeated the trick again and again and again. After about 10 cleavings, they transferred what was left onto a silicon wafer and looked under the microscope. What they saw was a fleck of graphite, so thin that the light from below shone right through it. When they zoomed in, they realized it was just one atomic layer, a single sheet of graphene. Until that moment, physicists believed a two-dimensional crystal could not exist at room temperature. Lev Landau and Rudolf Peierls had proved on paper, decades earlier, that it would melt instantly from thermal jitter. Geim and Novoselov had just held one in their fingers. 6 years later, in 2010, both of them flew to Stockholm to collect a Nobel Prize in physics. The official citation called it groundbreaking experiments regarding the two-dimensional material graphene. It was the fastest a discovery had ever gone from lab bench to Nobel, and the race was on. So what is it about graphene that broke so many records all at once? Start with the structure. Each carbon atom bonds to 3 neighbors in a perfect hexagonal grid. That bond, the carbon-carbon bond, is the strongest chemical bond we know of in nature. Pull on a defect-free sheet, and you'd need 130 gigapascals to snap it. In plain English, a sheet of plastic wrap that thin would hold up a full-grown elephant. Now look at electricity. In graphene, electrons don't bounce. They fly, behaving as if they have no mass. Electrons in graphene travel 100 times faster than electrons in silicon. They obey relativistic equations more familiar to particle physicists than chip designers. Heat moves through it as fast as anything we have ever measured, better than diamond, better than copper. And it is almost perfectly transparent. A single layer absorbs just 2.3% of the light hitting it. It is impermeable. No gas, not even helium, can pass through a perfect sheet. It bends, folds, and stretches by up to 20% without breaking. It is the strongest, thinnest, most conductive, and most thermally efficient material humans have ever made. Every one of those records was first measured in the same Manchester basement. But here's the catch that defined the next decade. Graphene has no bandgap. That missing bandgap meant graphene couldn't be switched off, and that's a problem for transistors. So researchers started looking past graphene at every other crystal you could peel. They found a whole family, sister materials with the same flatland geometry but very different rules. First in line, hexagonal boron nitride, chemically almost identical, but a perfect insulator instead of conductor. Researchers call it white graphene. It's the substrate every 2D experiment now sits on. Next, molybdenum disulfide, a natural semiconductor with a bandgap graphene lacks. It belongs to a class called transition metal dichalcogenides, TMDCs for short. Stack them just right, and you can build a transistor the size of a single molecule. Then there's black phosphorus like graphene, but with a tunable bandgap that depends on how many layers you stack. And the M-zenes, flat sheets of titanium carbide and similar metal compounds that conduct better than most metals. Plus silicene, germanine, steinine, boraphenine, single-atom sheets of silicon, germanium, tin, and boron. None of these exist naturally as flat sheets. We grow them atom by atom in vacuum chambers. Stack two of them on top of each other, and the rules change again, completely. The result is a new field called van der Waals heterostructures, designer materials built like Lego. You pick the properties you want, and then you literally build the material to match. In 2018, a young MIT graduate student named Yuan Chao tried something audacious. He took two sheets of graphene, laid one on top of the other, and rotated the top one by 1.1 degrees. That tiny twist created a giant moire pattern, a brand new superlattice on top of the original. At low temperatures, the whole thing turned into a superconductor, zero electrical resistance. Two sheets of carbon, the same element as pencil lead, behaving like a high-energy quantum metal. That single twist angle is now called the magic angle. And the field it opened is called Twistronics. What does it mean? It means the macroscopic geometry, not the chemistry, controls quantum behavior. It means you can dial in superconductivity, magnetism, or strange new electronic phases just by turning a knob. In 2025, follow-up experiments at Princeton and MIT confirm the effect is real and tunable. Layer 3 sheets and twist 2 angles, and you get a magic continuum, a whole landscape of new states. This wasn't just a discovery. It was a blueprint for a kind of materials engineering we never had before. Quantum behavior built to order from the geometry up. The catch is that magic angle physics only shows up at temperatures near absolute zero, for now. But the lessons translate. The same trick now works in twisted bilayer molybdenum disulfide, twisted boron nitride, twisted everything. Material science just turned into a precision tool with an angle dial. Meanwhile, the original holy grail had never gone away. Replace silicon. For 60 years, silicon has been the backbone of every chip in every device on Earth. But silicon is running out of room. The smallest transistor features are now just a few atoms wide. Below about 3 nanometers, silicon starts losing the ability to switch reliably. In January 2024, Walter DeHeer's team at Georgia Tech and Tianjin University changed the game. They grew graphene directly on a silicon carbide wafer and gave it a real, usable bandgap. They called it epigraphene, the world's first functional semiconductor made of graphene. And it works with the same manufacturing equipment chip foundries already own. That last detail is the kind that changes industries. Electrons in epigraphene move 10 times faster than electrons in silicon at room temperature. That could mean smartphones that are 10 times faster or use 10 times less power at the same node size. The team is now scaling up to wafer-scale production with industrial partners. But silicon won't be dethroned overnight. The transition will be a decade, maybe 2. In the meantime, graphene is already inside the chips you own as heat spreaders, sensors, and interconnects. You're almost certainly using it right now to watch this video. The first place graphene hit consumer products wasn't chips. It was batteries. Every lithium-ion battery you own is a sandwich of electrodes separated by a thin liquid electrolyte. The faster lithium ions can hop between those electrodes, the faster the battery charges. Add a thin sprinkling of graphene flakes, and suddenly the electrode is a quantum highway. Samsung's graphene ball cathode boosts lithium battery capacity by 45%, and it lets the battery charge 5 times faster, 12 minutes to full. Tesla has begun adding graphene conductive additives to the cathodes of its newest cells. The result is electric vehicles with longer range, lower weight, and far longer cycle life. Beyond batteries, graphene is also enabling supercapacitors, devices that store charge by surface area, not chemistry. A single gram of graphene unrolled flat has the surface area of half a tennis court. Pack that into a coin-sized device, and you can store a kilowatt, enough to start a car. Lighten, a California startup, just opened its first commercial 3D graphene production line for racing car components. Their first products are battery anodes and ultralight structural panels for motorsport. Add it all up, and graphene is quietly making the most ordinary devices in your life work a little better. You won't see it. You'll feel it in battery life, in heat, in speed. Graphene's biggest impact, though, might be on things you don't usually associate with electronics: water and concrete. Start with water. 2 billion people on Earth still lack access to safely managed drinking water. Desalination, turning seawater into fresh water, is the most reliable solution we have. But it costs enormous amounts of electricity to force seawater through traditional plastic membranes. Graphene oxide membranes change the math. Tiny nanochannels let water through, but block salt and contaminants. At pilot scale, they cut desalination energy use by up to 50%. And new variants now remove PFAS, the so-called forever chemicals that ordinary filters can't catch. Now switch to concrete. It's the most used construction material on the planet, and the second biggest source of industrial CO2. Adding tiny amounts of graphene to cement makes it stronger and lets you use less of it. The University of Manchester poured the world's first commercial graphene-enhanced concrete slab in 2021. They called it Concretine. It uses 30% less cement for the same strength. That single substitution could cut global concrete emissions by hundreds of millions of tons a year. It also makes the concrete more crack-resistant and corrosion-resistant, meaning longer-lasting roads and bridges. Graphene-enhanced asphalt, paints, coatings, and even sports gear are now shipping in production volumes. This is graphene's quiet revolution, not in the lab, but in the dull industrial backbone of civilization. If graphene is this magical, you have to ask the obvious question: why isn't it everywhere already? Industry calls it the valley of death, the long stretch between a lab demo and a profitable product. For graphene, that valley turned out to be deeper than almost any material before it. Problem 1: making it at scale without breaking the magic. Pristine, single-crystal graphene is still extraordinarily hard to grow at wafer scale. Cheap industrial powders, graphene nanoplatelets, and graphene oxide work for additives but not for transistors. Problem 2: quality control. There is no single thing called graphene. Different makers produce different layer counts, defect densities, and edge chemistries, and call them all the same name. International standards bodies are still catching up, and the engineering uncertainty has slowed adoption. Problem 3: the gap between 2D materials and the insulators we have to pair them with. A May 2026 study from TU Wien warned that many candidate 2D transistors fail because of bad oxide interfaces. Hexagonal boron nitride solves it elegantly in the lab, but is itself hard to grow over large areas. Problem 4: the market. Existing materials are very good. Graphene has to be better and cheaper, not just better. That's why some of the most successful early uses were boring: heat spreaders, anti-corrosion coatings, conductive inks. But these unglamorous applications are exactly how the next wave funds itself. So where does this all go from here? 3 big bets are converging in the late 2020s. Bet 1: graphene semiconductors actually replace silicon in specialized chips by the early 2030s. Bet 2: graphene desalination membrane scale to industrial size and start to crack global water poverty. Bet 3: Twistronics turns into a manufacturing platform for quantum and AI chips. The ID Tech X forecast puts the broader 2D materials market at $2.7 billion by 2036. That number probably understates it. 20 years ago, the same forecasters underestimated lithium-ion by an order of magnitude. The pattern is familiar. Long, quiet years, then a slow accumulation of industrial wins, then sudden ubiquity. It happened with plastics in the 1950s, with silicon in the 1970s, with carbon fiber in the 2000s. Each one rewrote the world before most people noticed. Graphene and its flatland cousins look very much like the fourth name on that list. 22 years ago, two physicists peeled a flake of pencil lead and changed the science of materials forever. Today, that flake is everywhere. In your phone, your roads, your batteries, and soon, your chips. The flatland of two-dimensional materials is just getting started. If you found this useful, subscribe for more deep dives on the materials quietly reshaping the modern world. This has been Cipher Sci. Until next time, keep looking closer.